Okay, number one, what is the ion product constant for water? Well, the ion product constant is a constant, and it's called Kw, and it's 1 times 10 to the negative 14. Now, the the value for H plus and for OH minus must be constant. It must be it's called a product constant, and as one goes up, the other goes down. But the product of the two must be 1 times 10 to the negative 14. And as you know, for neutral water, the H ion is going to be 1 times 10 to the negative 7th, and the OH would be 1 times 10 to the negative 7th, and that would be 1 times 10 to the negative 14. But as one goes up, the other goes down. As one goes down, the other goes up. So just a couple of exponent rules that I'll be using quite a bit during this video, and that is a to the n times a to the m equals a to the n plus m. So if it were 10 to the negative 5th times 10 to the negative 9th, that would be 10 to the negative 14. And a to the n divided by a to the m equals a to the n minus m. So it would be 10 to the negative 14 divided by 10 to the negative 9th would be 10 to the negative 14th minus a negative 9, which would be 10 to the negative 5th. Number 2, calculate the hydrogen ion concentration, H+, for an aqueous solution in which the OH concentration is 1 times 10 to the negative 9 moles per liter. Is this solution acidic, basic, or neutral? So we want to find the H ion concentration. So we know, based on Kw, that the product of the H ion and the OH concentration is 1 times 10 to the negative 14. We know that the OH concentration is 1 times 10 to the negative 9. So you plug in the OH concentration and you divide 1 times 10 to the negative 14 by the OH concentration, and that's going to equal the H ion concentration of 1 times 10 to the negative 5th. And don't forget, moles per liter, that's what the bracket is, and moles per liter equals molarity. Now, number 3. Number 3, a liter of impure water has 1 times 10 to the negative 3 mole of hydroxide ions. So it's in a liter, and that's how many moles, so the molarity is 1 times 10 to the negative 3 molar. What is the concentration of the hydronium ions in this sample of water? So there's the hydroxide ion concentration. So it's 1 times 10 to the negative 3 moles per liter. The Kw is 1 times 10 to the negative 14. Solve for H ion. So again, number 3 is very similar to number 2. It's going to be the Kw divided by the OH concentration, and that's going to be 1 times 10 to the negative 11. So the H ion concentration equals 1 times 10 to the negative 11. Make sure you check that on your calculators and make sure that you can come up with the exact same answer. Now, number 4. Number 4 says, if the hydroxide ion concentration is 1 times 10 to the negative 10th molar, what is the pH of the solution? Well, we're not given the H ion concentration, we're given the OH concentration. So let's pick a method that's actually easiest. There are several, but this is, I think, the easiest method. We know the OH concentration is 1 times 10 to the negative 10 moles per liter. The POH, which would be the negative log of the OH concentration, would be negative log OH concentration, and that would equal 10. And I know that the pH plus the POH equals 14, so the pH equals 14 minus the POH, and 14 minus 10 would give you a pH of 4. Number 5. What is the hydrogen ion concentration if the pH is 3.7? What is the hydrogen ion concentration if the pH is 3.7? So, you know that the pH equals the negative log of the H ion concentration. The inverse of that function would be essentially simply you're raising everything to 10 to the x. So 10 to the negative x, I apologize. So the pH, the H ion concentration would be 10 to the negative pH. So 10 to the negative 3.7 would be, you'd round it to 2 times 10 to the negative 4 molar. Make sure you can double check on your calculator and get the same answer. See if you can get the same answer when you double check. Number 6. What is the hydrogen ion concentration if the acid dissociation constant is 0.0001 and the acid concentration is 0.01 molar? Now, let's remember something very carefully, and that is that a to the n raised to the m equals a to the n times m. 10 to the negative 4 raised to the 2 would be 10 to the negative 8th. You're multiplying the two exponents together. So now, number 6. Okay, let's just go back quickly and look at 6 again. What is the H ion concentration if the acid dissociation constant is 0.0001 and the acid concentration is 0.01 molar? Okay, number 6, there's two methods. First, let's review what we have. We're only given the Ka, which is 1 times 10 to the negative 4. And we're given the HA of 0.01 molar. HA just means, is a generic way of saying an acid, where H is the H plus, is going to become H plus, and the A is going to be A negative, which is simply any anion. Okay, so we set the equation. Ka equals H ion times the anion concentrations divided by the HA, or the undissociated acid concentration. So I plug in. I say the Ka is 1 times 10 to the negative 4, and I say the acid concentration is 0.01 minus X. In other words, it's going to be minus the X, minus the H ion concentration. In other words, some of that acid concentration will dissociate. Well, how much is going to dissociate? Not much, but some will. And so when you're finished with the equilibrium, you're going to have the HA minus that which dissociated. So that's why you have to put the minus X. The 0.01 is small, and the Ka, 1 times 10 to the negative 4, is also very small. So now we're simply going to plug in, and we're going to solve X using the quadratic equation. But I'm not going to do that. I simply wanted to show you that if the Ka were larger, in other words, 1 times 10 to the negative 4 is actually very small, and 0.01 is the acid concentration, is also very small. If those numbers are small, the amount of X is going to be very small. So 0.01 minus X is essentially going to be 0.01, because the numbers are small enough so the denominator can be simply only and specifically 0.01, not 0.01 minus X, 0.01. So let's look at the next slide, which will show you that. So by the way, unless you're told otherwise, you have to assume that everything is a monoprotic acid, and otherwise they would say that it's not monoprotic. So, in other words, it's not H2SO4. It's not H2S. It's like, for instance, it could be acetic acid, where it's H and then C2H3O2, where that's the acetate ion. So you assume, unless otherwise noted, that it's a monoprotic acid. So that's the equation. Ka equals x squared over Ha. Plug in 1 times 10 to the negative 4 for Ka, 0.01 for Ha, and then multiply the 2. You get 1 times 10 to the negative 6. Then take the square root of both sides. X equals 0.001, or the H ion concentration equals 0.001 molar. Make sure you can get all of that on your calculator. Number 7 is going to be very similar. What is the concentration of undissociated acid if the hydrogen ion concentration is 0.0001 molar and the acid dissociation constant is 1 times 10 to the negative 7? So you see the Ka is very small, but now what you're going to calculate is you're going to calculate the Ha in the denominator. So, and remember, the numbers are very small. You can see that the H ion concentration is 1 times 10 to the negative 4. Ka is 1 times 10 to the negative 7. And remember that the H ion concentration and the anion concentration for monoprotic acids are equal. So, you plug in, look at your equation. Ka equals H ion times anion divided by Ha. Plug in 1 times 10 to the negative 7 for the Ka. Plug in 1 times 10 to the negative 4 for the H ion concentration. You can square that and then simply solve for Ha. So simply solve for the Ha, and you'll find that the Ha equals 0.10 molar. Make sure you can get that. Make sure that you understand how to calculate Ha and you understand the mathematics involved. Okay, let's do number 8. Number 8 says a 0.500 molar solution of a weak acid, Hx, is only partially ionized. The H ion concentration was found to be 3.86 times 10 to the negative 2 molar. Find the dissociation constant for this acid. Now, there's a hint in that problem, and that is that it says right away that it is a weak acid. It starts off by saying a 0.500 molar solution of a weak acid. Now you can see that it's monoprotic because it's Hx. They put Hx, I put Ha, it's the same. Is only partially ionized. Okay? Find the dissociation constant for this acid. So, this is method 1. I just want to show you, and without using a quadratic formula, how to do this 2 different ways. So, method 1 says the Hx concentration is going to be 0.500 molar. The H ion concentration is 3.86 times 10 to the negative 2 molar. Therefore, the anion concentration, or x to the negative 1, would be the same as the H ion concentration, which is 3.86 times 10 to the negative 2. So, you plug into your equation, which is Ka equals H plus times x negative divided by Hx. Plug into the equation as I've done and solve for Ka. you can clearly see that you square the numerator and simply divide by the denominator, and you get 2.97 times 10 to the negative 3. So keep that in mind when we look at method 2. We calculated 2.97 times 10 to the negative 3. But what happens if you do it a more accurate way and you subtract the point from 0.500 molar, you subtract the H ion concentration, which is the dissociated H ion concentration, and so at equilibrium, your acid concentration will be a little less based on subtracting off the amount dissociated. So as I do method 2, I am going to subtract off from 0.500 the H ion concentration, which is 3.86 times 10 to the negative 2, and we'll see if we get a big difference in the Ka. And I'll show you that indeed, it's really not. You can see that Ka rounded is 3 times 10 to 3.0 times 10 to the negative 3. So it's not going to be a big deal. So let's look at method 2 and subtracting off the H ion concentration. And there it is. So you're going to get 3.23 times 10 to the negative 3, which is really not very big. It's not. So you're okay. Now, I just want to say one thing about this subtracting off x from the denominator. Don't worry about it. Even in AP chemistry, you don't really have to worry about it. Rarely do you have to worry about it. Maybe you do one problem as practice. It's not a big deal. It's not going to be on your test. You don't have to worry about subtracting x off. But understand this. This is all you have to understand. Understand why you would want to possibly subtract the X or the H ion concentration from the undissociated acid concentration. If you understand why, then you're okay. You're okay. In AP chemistry or regular high school chemistry, it's not a problem. But please don't worry about it. Just simply do not subtract the X from the denominator, and you're going to be fine. So number 9, what is the acid dissociation constant of a weak acid? If a concentration of 0.2 molar gives a hydrogen ion concentration of 0.001 molar. And again, we're going to try to do not subtracting X from the undissociated acid concentration, and we'll do it by subtracting the X and see if, and we're just going to continue to see if it's a big deal. Remember, you don't have to do it, but you have to understand why, and why you would subtract the X, and why it really doesn't matter if you subtract the X if they are truly weak acids. So, number 9, method 2. That's the best. Okay, that's the most accurate. I get it. It says the Ka is what we're looking for. The acid concentration is 0.2. The H ion concentration is 0.001. Plug in 0.001 squared divided by 0.2 minus the 0.001, which is the H ion concentration, and you're going to get 5.03 times 10 to the negative 6. Understood? Make sure you get that on your calculator. Make sure you can do it. And then the method 1, which is the better method, I think. It's easy, and that's simply this. And that is that if I take 0.001, square it, divided by 0.2, and not subtracting off the H ion concentration, I get 5 times 10 to the negative 6. So you see, it's okay. It's okay. It's not a problem. So 5.03 times 10 to the negative 6 is certainly close enough to 5 times 10 to the negative 6. This method is okay to use always, really, but only for weak acids, very weak acids. Okay, number 10. Calculate the acid dissociation constant of a weak monoprotic acid if a 0.6 molar solution of this acid gives a hydrogen ion concentration of 0.001 molar. Okay, very simple. Again, we're not going to subtract it off this time. We're just going to do it once and plug in your values. 0.001 molar for the H ion concentration, which is the same as the negative X concentration, and that's going to be squared and then divide by 0.6, and you get 1.7 times 10 to the negative 6. Very simple, very easy, not a problem. Remember, it said it was a weak monoprotic acid, so you're in good shape with that. And I would use this method. Don't worry about subtracting X. Use this method and you're going to be just fine. Number 11, if the hydrogen ion concentration is 10 to the negative 9th molar, what is the pH of the solution? And you know that that would be 1 times 10 to the negative 9th. But 1 times 10 to the negative 9 is the same as 10 to the negative 9. And problems 11, 12, 13, 14, 15 are going to be very easy as opposed to some of the ones we've done up to this point. And so, number 11, you know that the pH equals the negative log of the H ion concentration. So the H ion concentration is 10 to the negative 9. So the pH equals negative log of 1 times 10 to the negative 9. Calculator check, and you're going to get a pH of 9. And then it says if the hydroxide ion concentration is 1 times 10 to the negative 11 molar, what is the pH of the solution? So again, this is kind of going back to the first couple of problems where I think the easiest way to do this is to calculate the pOH and then calculate the pH. So the pOH is the negative log of the OH concentration, so it's going to be pOH equals negative log of 1 times 10 to the negative 11, which is 11. You know that the pH and the pOH have to equal, so if the pOH is 11, the pH is 3. Number 13, if the OH concentration is 1 times 10 to the negative 5th, what is the pH of the solution? Very simple. We really just did this. We'll do it again. So let's wait for it. And it says, just go through this. It's the same. Remember, the pOH and the pH have to equal 14. So if the pOH is 5, the pH is 9. 14, what is the pH of a solution with a concentration of 0.01 molar hydrochloric acid? A little bit of a trick question. The hydrochloric acid completely dissociates, so the H ion concentration is going to be equal to the original acid concentration, which is 0.01. So it's going to be negative log of 0.01 is going to be your pH. If you put that into your equation, you'll get a pH of 2. Number 15, what is the pH when the hydrogen ion concentration is 1 times 10 to the negative 3? And if you're starting to get this now, if it's 1 times 10 to the negative 3, then it would simply be the negative exponent, because that's actually your log. So, but if you plug it in your calculator, negative log of 1 times 10 to the negative 3, you'll get 3. Okay? So that's it. That's a nice little review for you. Make sure that you can get all of these values on your calculator. That's very, very, very important, and that you understand it. Now, I wanted to give this to you early, so I'll be there all week. So ask me any questions you might have about this particular video and doing these particular problems. Again, don't get worried about the denominator. Just don't subtract the x. When in doubt, don't subtract the x from the denominator.